To understand the limits of modern memory density, we must look past the architecture of a microchip and examine structural constraints at the subatomic level. This 3D schematic shows a standard spin-orbit torque MRAM device. The architecture relies on a 3-layer stack: tungsten, cobalt iron boron, and magnesium oxide. A write operation begins when a charge current enters the heavy metal tungsten layer. Notice how the charge current immediately splits. The spin Hall effect inside the tungsten converts this charge into a transverse spin current, accumulating spin polarization at the interface to flip the magnetization of the adjacent cobalt iron boron layer. Generating this spin polarization dictates a rigid physical requirement. The base material must possess strong spin-orbit coupling. Strong spin-orbit coupling is found almost exclusively in heavy metals, like tungsten or platinum. These heavy metals inherently suffer from high electrical resistivity. Pushing the necessary current through a highly resistive heavy metal generates excess heat and drains power. In large-scale integrated circuits, this thermal and power draw creates a hard physical bottleneck for energy efficiency. Bypassing this bottleneck requires looking at the electron itself. Alongside spin, electrons carry an orbital degree of freedom, an orbital angular momentum that can be manipulated independently of its spin. By utilizing wave-vector-dependent orbital angular momentum, device engineers can generate the required transverse currents without relying on spin-orbit coupling. This physical substitution allows memory architectures to drop highly resistive heavy metals in favor of light metals like titanium, vanadium, or chromium. These highly conductive materials drastically reduce the power required for a switching operation. Pushing non-volatile memory density past its current limits requires abandoning spin-orbit torque and physically restructuring the device to harness pure orbital currents. Generating these pure orbital currents relies on two primary physical mechanisms: the orbital Hall effect and the orbital Rashba-Edelstein effect. This split-screen diagram contrasts the traditional spin Hall effect on the left with the orbital Hall effect on the right. On the left, the dark blue charge current produces transverse spin currents. On the right, the exact same charge injection generates a transverse orbital angular momentum current. Looking closely at the right side, the orbital Hall effect pushes the orbital angular momentum in positive and negative y directions. The physical geometry exactly mirrors the spin process, but it dictates the flow of a completely different quantum property. This separation of trajectories originates strictly from momentum space orbital texture. This orbital texture is highly robust. It exists across quantum systems, even when those systems perfectly preserve both time reversal and inversion symmetries. Because the separation is driven by orbital texture, spin-orbit coupling is entirely absent from the generation phase. The orbital Rashba-Edelstein effect operates on similar principles to create a non-equilibrium orbital angular momentum density, but it specifically localizes this density at the two-dimensional interface of a non-magnetic material. Removing the spin-orbit coupling constraint completely frees the architecture. It permits the integration of highly conductive light metals into the base layer. Generating the angular momentum is only the first step. Transporting this orbital current through the crystalline lattice introduces a direct contradiction with established condensed matter physics. Relying on momentum space texture instead of spin-orbit coupling successfully resolves the generation problem, clearing the main thermodynamic hurdle of traditional MRAM. Once it is successfully generated, the pure orbital current must carefully propagate through the dense crystalline lattice to reach the magnetic layer. In theory, orbital currents face an immense dissipative force during transport, crystal field coupling. This chart compares the energy scales governing dissipation. Traditional spin transport degrades via spin-orbit coupling, which operates between 10 and 100 millielectron volts. Crystal field coupling, which dissipates orbital momentum, operates at roughly 1 electron volt. The mathematics of this Hamiltonian are clear. A 1 electron volt interaction should cause immediate orbital quenching, forcing the electron to exchange its momentum with the lattice and dissipate the current. Empirical measurements actively contradict this mathematical expectation. Measurements using the magneto-optical Kerr effect to image thin films reveal that orbital currents actually travel through ferromagnets over vastly longer distances than their spin equivalents. Reciprocal orbital pumping experiments, which convert orbital momentum back into charge to measure its strength, corroborate these unexpectedly long transport lengths. The survival of orbital angular momentum across extended diffusion lengths, despite moving through massive 1-electron-volt crystal fields, is a severe physical paradox. It is an anomaly that engineers must harness, even as theorists work to explain it. Even with successful generation and transport, the architecture faces a strict limitation at its destination layer. Pure orbital angular momentum cannot directly flip a conventional spin-based magnetic moment. To exert magnetic torque, the orbital current must physically transform into a spin current. This conversion step is mandatory. The first pathway for this transformation is intrinsic conversion. This occurs natively inside ferromagnets with specific symmetries, such as nickel or nickel-iron alloys, where the material itself handles the translation from orbital to spin momentum. The second pathway is interfacial conversion. This utilizes a distinct inserted conversion layer sandwiched between the non-magnetic generator and the ferromagnetic target. Materials with extremely high spin-orbit coupling, such as platinum or 4F transition metals, act as highly efficient transducers for the specific orbital-to-spin conversion. The viability of this decoupled architecture was proven by a specific physical anomaly involving copper oxide. Early heterostructure experiments utilizing a stack of thulium iron garnet, platinum, and copper oxide observed inexplicable 16-fold enhancements in spin torque. Modern analysis resolved the anomaly. The copper oxide, despite lacking any spin-orbit coupling, was acting as a massive orbital current generator. The thin platinum layer was silently capturing that orbital current and acting as the spin converter. This proved that the two variables, generation and conversion, do not need to exist in the same material. They can be optimized in completely separate layers. Realizing a practical orbitronic device requires a highly engineered bipartite stack, a thick, low-resistance light metal strictly for generating the orbital current, paired with an ultra-thin interfacial converter to apply the torque. Commercial AMRAM integration demands specific mathematical thresholds. The dimensionless torque efficiency parameter, psi, measures generated torque against current density. Baseline spin-orbit stacks and early orbital stacks see psi plateau around 0.4. To achieve commercial viability, this efficiency parameter must double, exceeding 0.8. The primary structural roadblock to hitting this target is maintaining compatibility with high tunneling magnetoresistance. High SOC ferromagnets like nickel-iron excel at intrinsic conversion, but they possess large damping constants. This makes them physically incompatible with high tunneling magnetoresistance interfaces. To preserve the necessary coherent tunneling of a magnesium oxide barrier, researchers must force substantial orbital torque into body-centered cubic ferromagnets, specifically cobalt-iron-boron. The architecture that maximizes the torque efficiency parameter without degrading the cobalt-iron-boron and magnesium oxide tunneling interface will define the next phase of memory scaling. Beyond the material composition, fabrication faces a final geometric hurdle. The heterostructures currently demonstrating strong orbital torque rely on layers that are physically too thick for commercial CMOS nodes. Device engineers must artificially shorten the orbital angular momentum diffusion length. Constraining this transport minimizes the total material volume required to execute a low-current write operation. Resolving these material science challenges directly translates to significant energy and thermal efficiency gains for large-scale integrated circuits. Remaining tied to high resistivity heavy metals and standard spin-orbit coupling ensures a hard thermal and electrical ceiling on integrated circuit evolution. Transitioning away from traditional spintronics to master momentum space orbital texture provides a technically rigorous path towards sub-nanosecond, high-density non-volatile memory.